Thanks to Brilliant for sponsoring today's video. Today I've got a really interesting video about trees, leaves, and the number E. So what's a tree? Well, it's a type of graph, or at least in our setting it's a type of graph. Obviously it's also a potentially very large plant. Okay, so a tree is a graph so that if any edge is removed, it becomes disconnected. And then there's a certain part of a tree which will be important, and that's a leaf. And so a leaf is a part of a graph, but it's also something that generally grows on plants. So a leaf is an end vertex. So in other words, it is only connected to one other vertex. Okay, so let's look at some examples of trees. So there's probably an empty tree on 0 vertices and also a really simple tree with only one vertex. Perhaps that would be like an acorn. And so we're going to start our examples on 2 vertices. And in all of these pictures, I've labeled the leaves in green. So let's look. We've got a single tree with 2 vertices. And so both of those vertices are leaves, kind of obviously. Notice if we were to remove that edge, we would just have 2 floating vertices, and that would be obviously disconnected. So there's also only one tree on 3 vertices. And notice this inner vertex is not a leaf because it's not on the end. It's not connected to only one other vertex, it's connected to 2. Furthermore, if we remove this edge, it's obviously disconnected, and if we remove this edge, it's also obviously disconnected. So there are 2 trees on 4 vertices. There's this one which is really kind of an obvious extension of the top 2, and then this other one which kind of like branches off from a middle point. Then there are 3 trees on 5 vertices. So you've got this one which is just a long line, and then you've got this one that branches at the end, and then the one over there which comes out of one inner vertex. Again, notice that I have the leaves in green. Now, before we move on, I'd like to point out that a lot of these are so-called Dinkin diagrams for Lie algebras. So in fact, this is the Dinkin diagram for the Lie algebra A2, in other words, SL3. This is the Dinkin diagram for A3, in other words, SL4. This is the Dinkin diagram for A4, in other words, SL5. This right here is the Dinkin diagram for D4. So D4 is the only Dinkin diagram that has this like triality. This automorphism group which is not Z2, it's in fact S3. Then down here we have the Dinkin diagram for A5. This is the Dinkin diagram for D5. That last one, it's not a Dinkin diagram for a finite dimensional Lie algebra. It might be a Dinkin diagram for an affine Lie algebra. I think it might be a Dinkin diagram for affine D4, although, I'd have to look that up. Maybe post in the comments if you know if that's a Dinkin diagram for one of the affine Lie algebras. Okay, so that being said, I think maybe I could give you a little homework exercise right now of finding all of the trees on 6 vertices. 6 vertices is maybe the largest number where it's really worth it to draw all of them. In fact, you can check that there are 6 trees with 6 vertices. Okay, so now let's move on to the question of how many trees are there on n vertices? If you're looking for a free and easy way to learn more about graph theory, check out Brilliant.org. Brilliant offers a wide range of topics for all skill levels, from beginner to advanced. With Brilliant, learning is not just easy but exciting. Take a quick quiz and Brilliant will customize content to your interests and skill level, maximizing your time. What really makes Brilliant shine is its problem-solving approach. You won't just passively absorb information, you'll actively learn through hands-on interactive lessons that challenge your thinking and creativity. Also, Brilliant's available on your phone, tablet, or computer, so you can use it anywhere, anytime. Not sure where to start? Well, if you liked today's video, you could check out their Introduction to Computer Science class. Graph theory is a really important part of theoretical computer science, and there's graph theory explored in that course. Keep your love for learning alive with Brilliant's interactive lessons where learning is a destination, not just a journey. It really is great for everyone. I use it to stay sharp, and my son loves it to keep ahead in math at school. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself this holiday season to a unique hands-on experience by going to brilliant.org/MichaelPenn for a 30-day free trial, and the first 200 people will get 20% off their annual premium subscription. Thanks once again to Brilliant for sponsoring today's video. So I've got some bad news if you wanted a closed form for the number of trees within vertices, because it's well known that there is no closed form for this number of trees. That being said, Reshetnikov in 2016 proved that the number of trees within vertices is equal to the number of ways to arrange n-1 non-intersecting circles on a sphere. And we're not going to look at this very closely, but maybe we'll look at the case when we have 3 vertices in the tree, which means we're arranging 2 non-intersecting circles on a sphere. So this result says there should only be one way to do that, you know, based off the fact that we wrote all of the 3 vertex trees on the last board. So maybe I could see one way of doing this like this. We could put a circle up here, and then we could have put a circle down here. But that being said, I think there's maybe another way that looks obvious, which would be to put a circle right here and then a circle down here. But you can actually prove that those are the same, and we're not going to go into a ton of detail with that because this isn't really the point of the video. But you can maybe stretch parts of this sphere and collapse parts of this sphere to turn this picture into this picture. And that's really what makes these non-intersecting circles on a sphere different than non-intersecting circles in a plane. You have like a lot more liberty as to when you can stretch the circles into each other or out of each other. Okay. So anyway, now that we've learned about trees, I'd like to talk about something called a labeled tree. Okay, so now we want to talk about something called a labeled tree. And you can label a tree a number of different ways, but we'll take the labels to be from a certain set. So here's the definition we'll use. So a labeled tree is a tree whose vertices have been labeled from the set 1, 2, 3 up to n, where each vertex has a different labeled. And I guess I should say here that we have a tree with n vertices. So you're labeling an n vertex tree from this set from 1 to n. Okay, so let's look at some examples. So let's say n is the number of vertices and a sub n is the number of labeled trees, because we're trying to collect these numbers a sub n. So let's look at n equals 2. Well, it might look like there are 2 ways to label this, with a 1 here and a 2 here, a 2 here and a 1 here, but we only take one of those. Because this tree is kind of living out here in the ether, it doesn't have like a direction to it. So if we were to draw this the other way, let's maybe put a bubble here. So if we were to draw this the other way like this, with a 2 here and a 1 here, we would see that as the same labeling. Again, because its orientation in space does not matter. Okay, so let's maybe move on to n equals 3. Actually, before we do that, let's collect this number. So this means that a sub 2 is equal to 1, because there's only one way to have a labeled tree with 2 vertices. Okay, so moving on to n equals 3. So we could have a 1 here, a 2 here, and a 3 here. That's maybe the obvious way to do it. So that's putting a 1 on an end vertex. We could also have a 1 here, a 3 here, and then a 2 here. So that's putting a 1 on the end vertex and a 2 on the end vertex. So notice that we can count these by which vertices are on the end. So here 1 and 3 is on the end, 1 and 2 is on the end. Or we could have 1 in the middle and 2 and 3 on the end. So that enumerates all of those. Again, it might look like there should be more, like 3, 2, 1, but that's the same as this 1, 2, 3 because of the directionality there. Okay, so putting this all together, what do we see? We see that A3 is equal to 3. Okay, so now let's move on to n equals 4. Maybe this type of n equals 4 is the easiest because each labeling is completely determined by which one's in the middle. So we could have a 1 here, 2, 3, 4. We could have a 2 here, 1, 3, 4. We could have a 3 here, 1, 2, 4. Or we could have a 4 here, 1, 2, 3. So we get 4 from that. Then how many do we get here? Well, we could always start with a 1 and then have 2, 3, 4. We could start with a 1 and have 2, 4, 3. We could start with a 1 and then have 3, 2, 4, and then you could go on and on and on. So you might think that there should be 4 factorial ways of doing this because there are 4 factorial ways of filling in those numbers, but because of the symmetry built into this, if we reverse one of these, it's the same. So in the end, there are 4 factorial over 2 total ways to have this type of labeled tree on 4 vertices. So in the end, from this shape, how many possibilities do we get? Well, 4 factorial is 24, divided by 2 is 12. So 12 total from here, and then obviously 4 total from over there. So putting that together, we have A4 is 12 plus 4, which is 16. Okay, so now let's see if we can see a pattern arising here. So let's look at A1. Well, could we write A1 some way involving 2? Yeah, notice that this is 2 to the 0. So obviously I know the pattern, so I'm working backwards from there, but I think like we can agree that 2 to the 0 is 1. But how can we write 3 in a way that matches with this pattern? Well, let's notice that 3 is the same thing as 3 to the 1. And then what about 4? Well, 16 is equal to 4 to the 2. So it looks like our base is the number of vertices that we have, and then the exponent is 2 less than that. So it seems like a sub n is n to the n minus 2. Okay, great. And so let's maybe see if we can prove that. So in fact, this counting of the number of labeled trees is something called Cayley's theorem. And so let's state it. So there are n to the n minus 2 labeled trees with n vertices. And there are several proofs of this. We're going to outline the proof given by proofer. And the idea is to transform a labeled tree into a sequence. And then count the number of sequences that we would get out of that. And we'll see that counting the number of sequences that we get out of that is fairly easy. Okay, so this has a 2-step process. Okay, so let's see, the first step is to remove the lowest labeled leaf and then append its neighbor to the sequence. So as you can see, if we remove the lowest labeled leaf, then we're going to shrink the tree, and then we append its neighbor to the sequence, we build the sequence. So we're going to continually shrink the tree and build the sequence. And so that brings us to our second step, which you might guess what it is, and that is just to repeat. And how long do we repeat? Well, we repeat until there are 2 vertices. And that's because once we get down to 2 vertices, well, there was only 1 labeled tree on 2 vertices, so we're done. Okay, so let's outline this idea with an example. And our example will start with a tree with 7 vertices. So let's get it drawn on the board. Okay, so there it is. We've got our 7 vertex tree. And notice we have 4 leaves in this case. We've got a leaf 2, 5, 7, and 6. So we want to look at the smallest leaf, and the smallest leaf here is leaf 2. So that means we're going to remove that, and as we remove that, we build our sequence. Okay, so let's remove this leaf. Okay, so we've just removed the leaf, and after removing the leaf, we append its neighbor to the sequence. So that there, we're starting our sequence. And now we continue that process. So let's look for the smallest labeled leaf now. Well, notice the smallest labeled leaf now is this leaf that is labeled 5. So now we're going to remove that, and then add its neighbor to the sequence. Okay, so we remove it, and then adding its neighbor adds a 3 to the sequence. And now let's see where we are at this point. Well, at this point, we've got a leaf which is 7 and a leaf which is labeled 6. So obviously the leaf labeled 6 is the smallest labeled leaf. So we're gonna remove that and then append its neighbor to the sequence. But now this neighbor is a leaf. So let's maybe change that orange 4 to a green 4, just to exhibit that that's a leaf at this point. Okay, so again, we're gonna continue this process. Our smallest labeled leaf now is this 4. We're gonna remove that and then put its neighbor into the sequence. Its neighbor is 1. Oh, but 1 is a leaf now, so let's erase this orange and put a green in there. And then we only have one step left because now we've got 3 vertices. We know the next step will give us 2 vertices, which is our ending condition. So we've got our smallest labeled vertex is 1 in this case, so we're gonna remove that 1 and then add a 3 onto our sequence because that's the neighbor of 1. Okay, so we've done it. Notice that we started with a 7 vertex tree, and then this process gave rise to a sequence of 5 numbers from the set 1 to 7. Okay, so that is essentially our, so that's our transformation. So let's look at the result of this transformation. So this process builds a bijection from the set of labeled trees with n vertices to sequences of length n-2 from this set from 1 to n. And so we actually allow repetition over here in this sequence. And I think you might recall that the sequence that we built had repetition in it. It included, I think, a 1 and a 3 both twice. Now, I guess there's like a little bit more to check. You have to check that this is actually a bijection. We're gonna leave that off as it's not quite as fun as the experimentation that we've done so far. Now, we're just going to use this bijection to find this number right here by counting the number of sequences over here that satisfy this condition. But this number is fairly easy to calculate. So this is maybe clearly there are n to the n-2 of these sequences. Well, why is that? Well, notice our sequence is of length n-2, and each entry we have n choices. So totally we have n times n times n, n-2 times, giving us the result. But then the bijection tells us that there are the same number of labeled trees with n vertices, and that gives us Cayley's theorem. Okay, so let's go up and look at the title of this video, On Trees, Leaves, and E. Well, we haven't seen anything about E yet. Well, let's see how that's related. Okay, so to finish this up, let's look at the probability that there is a leaf labeled with 1. And so notice that this is pretty clearly going to be the number of trees where 1 is a leaf divided by, well, the total number of trees, where I guess I'm not writing labeled trees here, but that's our setting. We're looking at labeled trees. So obviously that denominator we know from, well, what we just did, and we know that this denominator is n to the n-2. So we just have to consider that numerator, and let's do it with a little bit of a picture. So let's say that we have a tree where one of the leaves is, well, the number 1. So let's put that as a leaf right here. And then let's maybe say, okay, that's going to be connected to another vertex. And then kind of built off of this other vertex is a large tree. But what do we know about that tree? Well, we know exactly how many vertices it has. So this is a tree with n-1 vertices. And I guess these n-1 vertices are labeled with 2, 3, up to n. Okay, nice. But now we can do a little bit of counting here. So how many trees are there with n-1 vertices labeled 2 to n. Well, notice that we could just subtract 1 from that, and it's exactly Cayley's theorem. So there are exactly n minus 1 to the n minus 3 such trees. But that's not quite everything. And that's because this vertex, well, this vertex could be a 2, it could be a 3, it could be a 4. Well, actually, it could be any number between 2 and n. So that means there are n minus 1 possible labelings for this vertex. In other words, there are n minus 1 possible, like, different connection points to our leaf, which is a 1. Okay, so now we're ready to finish this problem over here. So the number of trees where 1 is a leaf. Well, we have n minus 1 ways of choosing the connection point to 1. And then after that, we have to build a tree. But there are n minus 1 to the n minus 3 ways to build that tree. So let's write that down. And this is all over n to the n minus 2. But let's look at this. We can rewrite this as n minus 1 to the n minus 2 over n to the n minus 2 just by multiplying out that numerator. But now the numerator and the denominator have the same exponent, so we could potentially simplify this down to something like 1 minus 1 over n to the n minus 2. But anytime we see something like that, that kind of obviously has a limit, we might as well take the limit. And let's notice that if we were to take the limit here as n goes to infinity, we get the number 1 over e. So that's how we have a connection with e here. So for a large value of n, the probability that you find 1 as one of the leaves is approximately 1 over e. And this thing converges, I think, quite quickly. So it doesn't take long to maybe get to that point where you're pretty close to 1 over e. And that's a good place to stop.